Many of you would come from the old legacy instrumentation where we would have different types of signals. And the purpose of this recording is just to show you why the 4 to 20 milliamp became the decided choice of those. So I have gone and marked out our choice of 4 to 20 milliamps. In the late 70s and early 80s, the first choice for an instrumentation signal fell into the 0 to 10 volt range. Imagine if you had a tank and you had an instrument, and that instrument just had to send a signal to a control room on the other side. Now, it all sounded simple enough. If you possibly had a level inside the tank, and let's go and say that that level was going to be at 75%, well, then the easiest thing was just to go and say 75% would be equal to 7.5 volts. So if we were to send 7.5 volts DC from the instrument to the control room, that 7.5 volts would get to the other side, and that would give us an indication of 75%. Nice and straightforward, apart from the fact that we can have a voltage drop that is going to occur on the line from the one side to the other, especially over the longer cables. Now, the disadvantage over there is that that 7.5 volts might drop down to 6.8 volts. And 6.8 volts means that you're going to have a level indication of 68%. And that's not going to be good to anybody because it then becomes an inaccurate reading. So what is the easiest solution then going to go and be? Well, for all intents and purposes, if you go back to your days at university or college, you would recall that if we have a supply of voltage, and if I was to go and have numerous sources of resistance put into a circuit, then the basic rules say that the current which flows in any point in that circuit is going to be exactly the same as a current flowing in another point of the circuit. It's very easy to do. You go and get the total resistance of your circuit and you divide that into the voltage, and that's going to give you the current that is going to go and flow. So the current at that point is going to be exactly the same as the current at that point and the current at that point. Yes, according to Kirchhoff's current laws, that current is going to split up into two currents. But the two currents come back together and form a single current. And so we're going to have the single current that will flow through the whole circuit. Now we know that it's going to be easy enough to go and do that. So what actually happens is that the instrument does something very, very interesting. In the case of the instrument, that instrument will receive a source of power. Let's just go and draw the instrument in over there. And that instrument will look at the conditions that it is subject to, whether that be level, pressure, temperature, flow, whatever the case would be, and it will go and change its internal impedance up and down so that we're still going to get the correct milliamps signal that is going to go and flow through it. In the early days, they would have had a 0 to 20 milliamp, and that would have progressed to a 4 to 20 milliamp signal. Let's go and explain that difference to you quickly. I have put up two scenarios for you. On the left-hand side, there would be an instrument with a 0 to 20 milliamp signal. And on the right-hand side, there would be an instrument with a 4 to 20 milliamp signal. Now, let's go look at that one on the left-hand side. 0 milliamps is going to represent 0%. 5 milliamps would be 25%. 10 milliamps, 50%. 15 milliamps, 75%. And 20 milliamps would be 100%. So nice and easy as far as those divisions are going to be concerned. The only problem is, if I was to have a problem in the plant, such as maybe a large rat that broke into my plant, and that rat of mine came and chewed off the cable at that point, there's going to be no flow of current. Now, no flow of current says that the instrument in the control room is going to show 0%. And all that's going to happen is that my operator is going to imagine that I'm sitting at the lowest level possible. The tank is empty or whatever the case. On the right-hand side, you can see where we can improve on this. In the case of a 4 to 20 milliamp signal, please have a look at how the 4 milliamps is equal to 0%. 8 milliamps would be 25%, 12 milliamps 50%, 16 milliamps 75%, 20 milliamps 100%. So horror above horrors, if I was to have some other rat come and break into the plant and chew off the cable at that point, it's going to give me 0 milliamps, which on a tank of a 0 to 100% is going to show me minus 25%. Now, we cannot have a tank that's going to show us minus 25%. And in a case like that, your operator knows to immediately pick up the phone and call the instrumentation people, because there's going to be a major problem. So this is it. With the old legacy instruments, what we've just gone and shown you is how we have evolved from the voltage DC signal to a 0 to 20 milliamps to a 4 to 20 milliamps. And there are going to be other variations, of course, but that is as far as I will go today. Thank you.